Okay, great. So thanks for the invitation, and I'm sorry not to be able to be there in person, but this has to work. And so the topic here is probably a bit outside of the usual talks at the conference, but it does have something to do with sort of non-vacuum effects. And this is joint work with Marius and Jeremie, really the major part of the work was done by Marius and Jeremie, I have to say. And I should also say that I think you can think of this as this is somewhat formal, the results that we have. And I think you can think of it as sort of showing a direction of research rather than some, well-rounded analysis results, so to speak. But anyway, so what this, so what the talk is about is this is inspired by results on Maxwell equations and propagation of light, and so everyone knows geometric optics. So if you look at high frequency, infinitely high frequency, then light beams propagate along null geodesics. But if you take into account, effects beyond sort of order 1 over frequency, then you see other effects. And in particular, if you look at propagation of light in an inhomogenous medium, then the spin or polarization of the light couples to orbital angular momentum. And this gives rise to polarization-dependent trajectories. And this is the spin-Hall effect of light. So if in experiments you can see that light beams propagate in a way that depends on the polarization of the light beam. And this was observed, back in 2008. So the general situation, we have some small parameter, Planck's constant, 1 over frequency, wavelength, and we look at WKB ansatz, for example. And one of the classical results is that this Yegorov theorem, which says that if you look at semi-classical evolution, this is accurate to order epsilon for some, and this holds for some bounded period of time. But if you have a field with internal structure, then if you want to go higher in accuracy, you need to introduce corrections. And for a field like Maxwell, this introduces something that's known as Berry curvature. And there's a lot of work on these and related topics. But so this leads, so when you perform this analysis, you get modified equations of motion. So you no longer get the geodesic equations. And roughly speaking, these modified trajectories, the deflection of the trajectory is analogous to a spin-Hall effect, or it can be referred to as a spin-Hall effect. And we can apply this procedure to all sorts of different fields, Dirac, Maxwell, Yang-Mills, and GR. If you look at, there's a whole very, very large field of study which deals with the equations of motion for spinning particles or particles with some internal structure. And if you just look at the kinematics, then you get equations of motion for the position, the momentum, and the spin tensor. So these equations are just coming from the kinematic setup, so to speak. But to get the complete system of equations, so here there's no equation for the x dot, and that's in principle not exactly related to the momentum. So you need to complete the system to get a closed system of equations. You need a spin supplementary condition, and this spin supplementary condition is related to the choice of centroid of the wave packet. So here, so all of this has to do with essentially sort of localized wave packets and their propagation. And a lot of the work on this equations of motion, this MPD equations and so on, this is motivated to a large extent by the self-force problem in GR, which is is a very hot topic as far as analyzing gravitational waves from extreme mass ratio in spirals and so on. Yeah, so the general situation is that if you look at a higher order WKB for spinning fields, you can derive a system of MPD type with a specific SSC. And if you do this for massive Dirac, then that's analogous. The resulting equations are very analogous to the MPD equations for massive spinning particles. And the SSC is this Tulchev spin supplementary condition. And on the other hand, if you look at massless fields like Maxwell and GR, you get a different SSC. And here, this is an observer vector field. So there's a recent paper by Abraham Hart and Marius on this topic. So all of this fits in, all of these things sort of fit into this general scheme of MPD equations, which is not completely obvious from the beginning, so to speak. I also want to mention, so this is very closely related to high frequency perturbations in GR. And this was studied a long time ago by Isaacson and Oancea. Basically, this is also the fact that you can perform this analysis and get sort of consistent field equation for the limit of high frequency limit of the perturbations. This is deeply related to the fact that you have some null condition for GR. And one conjecture in this, or one idea in this area is called the Burnett conjecture. And basically the idea is that if you look at the high frequency perturbations on a regular background, the limiting field equation is like null dust. And this has been analyzed recently by Cécile Renaud and others, and also Igor and Jonathan Luck. And I also want to mention that when you can think of these things, both as in terms of wave packets. So the limit, the field equation that you get in the limit, really depends on the way you take this limit. So there's also close relation between these considerations and back reaction of inhomogeneities in cosmology. And I just mentioned Green and Wald as one example of a paper. And there are different regimes that you can look at, and the relation to actual observations in cosmology is quite subtle. And another direction is when you perform these types of limiting procedures, you can also get a Vlasov type equation, like kinetic theory as a limit. And there's a whole field of work relating to chiral kinetic theory, where you have not in the classical Vlasov, you have basically collisionless matter. The particles move along geodesics. You can have if you take the internal structure into account, you get modifications, and so you have sort of a spinning version of Vlasov, which is another interesting direction. Right. Okay. So I just want to quickly remind you what the Hall effect is. So if you have a current through a conductor, I mean, this is sort of high school physics nowadays, right? And then you turn on a magnetic field, and you see a deflection of the electrons, and this results in a charge across the conductor, and so you then reach a steady state. So this is quite sort of very classical, and now there's a similar effect for if you take spin into account. Then, depending on the spin of the particles, they will be deflected in opposite directions. So you get a spin current transverse to the material, and this is a kind of this deflection of the spinning particles. This is analogous to the spin Hall effect for light, which you see in an inhomogenous medium. Okay, so the Maxwell field, I mean, that's a spin 1 field, so it has internal structure, and it carries both spin and orbital angular momentum. And what in this case, what you have is you have the potential for interaction, so you can so spin and orbital angular momentum are parts of the total angular momentum of the field. And for the total angular momentum, you have conservation laws, but in a general situation, if you have inhomogeneities and so on, the spin and orbital parts of angular momentum are not separately conserved, and so there can be a transfer of momentum from spin to orbital and vice versa. So there's a spin-orbit coupling, and this gives rise to the deflection of trajectories. And so this just illustrates that this has been observed, and the effect is of order 1 over frequency. So this is, if you only do geometric optics in the infinite frequency limit, you will not include these effects. Right. So a very important fact, if you look at relativistic fields, and in particular light, is that the centroid of a beam, the location depends on the velocity of the observer. So there's a transverse deflection of or displacement of the centroid for a beam of light, depending on the velocity of the observer. And this was discussed by Wigner, I think, before in the 1940s. And this type of effect is very closely related to the deflectional trajectories. Right. Okay. So Maxwell is a very classical theory, and so here are the field equations, and there is an action principle. This is the Lagrangian, or at least one version of the Lagrangian, the Schwarzschild action principle. And if you do perform the variation of, so there is one of the field equations is just coming from the fact that you have a potential for the field strength. So dF is 0, but from the varying the action, you get the other field equation, which is the divergence of F is equal to 0. So this is Maxwell in vacuum. Now, if you look at this spin one field, and you look at, you can have so the field can be polarized. So this means that the field is in an eigenstate of the spin operator. And so if you have a circularly polarized field, you have basically, since the spin is 1, so you have these two eigenvalues. And so you have you have left and right polarizations. But the field also has intrinsic orbital angular momentum. And this can be created, you can create beams with intrinsic orbital angular momentum by passing them through a suitable lens or optical plate here. So here, this just illustrates where you add one, you create sort of one intrinsic orbital angular momentum state. But you can prepare beams with, where this eigenvalue can be on the order of 10. Significant. This can be a significant thing in comparing to the spin eigenvalue, which has only the two possible eigenvalues. The intrinsic orbital angular momentum can take very large values, and you can have this spin orbit coupling, and you can also have coupling between intrinsic and extrinsic orbital angular momentum. So, and this can you can have orbit deflections coming from the intrinsic orbital angular momentum as well. Right. So this illustrates the fact that you have basically, formally you have an unbounded number of eigenstates for the intrinsic orbital angular momentum. And so this illustrates the extrinsic orbital angular momentum. So here you have this depends on basically on the location of the beam with respect to an observer. So here is now the decomposition of the total angular momentum into spin and intrinsic and extrinsic orbital angular momentum. And so it was only in the 1990s that it was realized that if you look at the propagation of light in Minkowski space, that these quantities are separately conserved. And I mean, so at least if you ignore this extrinsic, but the fact that you have the spin and orbital angular momentum are separately conserved. So it's a sort of textbook fact that they are not, but in fact, it's a deeper fact that they are in fact separately conserved in Minkowski space. And this insight was sort of necessary for the analysis that led up to the spin Hall effect of light. So since we have these several different parts of the total angular momentum, you can have coupling between those, and this gives rise to several different type of effects. So there are spin Hall effects when you go from you couple spin to extrinsic orbital angular momentum, and you can also have orbital Hall effects. And this is interesting because, as I said, the intrinsic right. So the spin Hall effect of light. This just refers to light propagating in an. This arises when you look at light propagating in an inhomogeneous medium, and you can analyze the equation of motion up to order 1 over frequency, and there's a significant term here that will modify the trajectory. And you can do a similar analysis where you look at intrinsic orbital angular momentum, and then you have the same type of equation, but now with spin replaced by spin plus intrinsic orbital angular momentum. Okay. And so now, if you look at light propagating in an inhomogeneous medium, this can be described by the vacuum equations, but in a curved metric, the Gordon metric, where the metric now depends on this optical index. And so, since the spin Hall effect of light has been observed for light in an inhomogeneous medium, you can imagine that there would be a spin Hall effect of light due to the gravitational field. So if you have light propagating in an inhomogeneous space-time, you would expect to see a deflection of the light trajectories, and this could be referred to then as the gravitational spin Hall effect of light. And so I just want to mention several papers here. So there's a survey paper that has been updated, but so this reviews. So there's been several different analysis of the gravitational spin Hall effect of light, which have come to somewhat, disparate conclusions. So so one needs to do a fundamental analysis, and so in this paper, which appeared in 2020, we did a covariant analysis of the gravitational spin Hall effect. And this pointed out the role of Berry curvature in this general relativistic setting. So the analysis is based on a careful WKB ansatz, and analyzing this to order, not just to the leading order in epsilon. And here epsilon is, plays the role of something like 1 over frequency or wavelength, but the scale is really set by the scale of the inhomogeneities in the space-time. And so there are a couple of later papers. So there's another paper on the spin Hall effect for gravitational waves, So here the helicity is, so the spin is 2, so you have these eigenstates for the helicity. I also want to mention this paper, which discusses the fact that this conservation of the separate conservation of spin and orbital angular momentum for Maxwell theory is also true for linearized gravity in the weak field situation. And so the structure of the theory, Maxwell and gravity, they're very, very similar in some sense. And here, in this analysis of the spin Hall effect for gravitational waves, which refers to the propagation of gravitational waves on an inhomogenous background, the resulting dynamics is essentially identical to the one that you get in the Maxwell case, with the exception, with the difference that this spin parameter it takes values plus or minus 2 instead of plus or minus 1. So this just reflects the different spins of the field. And so here in this analysis, the Berry curvature plays a very important role. And the Berry curvature this originated in an analysis of sort of adiabatic changes of states of a quantum system. And what it does is that it talks about the relative phase. So if you look at the quantum system, the phase of the system is in principle not observable, but the relative phase is observable, and that was Berry's observation, so to speak. That if you have a quantum system where the parameters are slowly changing, and if you change the parameter in such a way that you come back to the original parameter values, then and you follow the phase, then the phase change, or the relative phase, is an observable. and this can be, the amount of change can be understood by looking at this Berry connection and Berry curvature. Right. So this is analogous to if you look at parallel translation of around a closed curve in the sphere, then the total area inside the curve reflects this will tell you the amount of change in the parallel translation. And this is very closely similar situation to the effect of the Berry curvature, as you have a quantum system undergoing this slow change of parameters. And so this can be this type of thing appears in many different situations, and this also shows up in the spin Hall effect. So here are the Maxwell equations. We make a WKB ansatz. So here's so this script A here is the vector potential, and there's a polarization vector and the phase factor. And so everything here depends on the epsilon, and we have to look at not just at the leading order, but the next leading order in this amplitude. And here K here is the wave vector. So this is the gradient of the phase function, and the flow of this vector. This is basically the phase flow, which gives the geometric optics limit, so to speak. And if you have an observer vector field, the frequency that this observer will see will then be of this form. And if you make the WQB ansatz, basically the derivative is replaced by this IK over epsilon, which you see by applying derivatives to the ansatz here. So now we take this ansatz, plug into the Maxwell action, and use stationary phase, and then calculate. So with this ansatz, calculate the resulting action. You calculate the Euler-Lagrange equations up to order epsilon squared, and impose Lorentz gauge. So if you do this at leading order, you get you just recover geometric optics. So the light propagates along null geodesics, and the polarization vector, or this amplitude, just propagates along, just parallel propagates along those trajectories. So you find these relations. So if you write this amplitude in terms of the intensity and the polarization vector, then you have the following relations. So the polarization vector, the wave vector has to be null. The polarization vector has to be perpendicular to the wave vector, and the intensity propagates along the flow. And in particular, this has to be autoparallel. But now at first order in epsilon, you get that the polarization vector propagates along the flow, and you get this Hamilton-Jacobi type relation. And here the K here is contains now the wave vector sorry, and a correction term, which is of order epsilon. And so that's quadratic in the polarization vector, but it has this derivative in it. And the effective transport equation is then of this form. So now the intensity doesn't simply propagate along the wave vector, but if you take into account the higher order effects, it propagates along this effective wave vector. So to further analyze this, we introduce a null frame. So use the wave vector as one of the null legs. And here's another null leg, and then the two complex null vectors. And you expand the polarization vector out in terms of the frame and use the fact that it's perpendicular to K. So this means that the factor, the component along the other null vector, because the inner product here is 1 or -1 depending on the signature. You have only these components left over. So now, if you look at the propagation of a vector along, or a vector depending on the wave vector. So here it's important that these are not just vectors on spacetimes; they're really thought of as vectors on phase space. Then you can show that the propagation is really involving the horizontal covariant derivative, which has a correction term in the Christoffels involving, or it has a correction term involving the derivative in the momentum direction. And so with this horizontal covariant derivative, we can introduce the Berry connection, which is of this form. And if you perform a spin rotation of this null frame, then the effect on the Berry connection is a gauge transformation. So this looks like a sort of a U1 connection, so to speak. And you can normalize these coefficients Z1 to Z3 or Z1, Z2, and in particular the helicity. So this is just sort of unit normalization, and then there's the helicity that comes in. And if we have circular polarization, then the product of those is 0. So you're in a sort of pure state. Now, if you look at this Berry connection and integrate along a trajectory, you get the Berry phase, this. You can then introduce a non-local phase function which modifies the phase function in the ansatz, and you can derive an effective Hamilton-Jacobi equation involving this non-local phase. And this effective Hamilton-Jacobi equation is then used to derive the modified trajectories. And so after some manipulations, you get then you can introduce these new variables, and you get a system of an equation of motion for these variables with the parameter epsilon in front of these modifications. And so these quantities F here involve the Riemann and Berry curvatures. So, for example, some of those take this form. So here is the Riemann curvature showing up, and here's the essentially Berry curvature showing up. So, and then putting all this together, you get equations of motion, which, if you look at the leading order term here, this is just the geodesic equation. But at order epsilon, we have these corrections, which somewhat resemble the equations that you get for a charged particle moving in an electromagnetic field, but they're also terms involving space-time curvature like this. And then you have the polarization. This Z here sort of reflects the state of the polarization, and this undergoes motion where the Berry connection comes in. And so here, as I said, so you can perform this analysis for Maxwell or linearized gravity propagate in a curved, in an inhomogenous background. And you get essentially the same system of equations of motion, but with the parameter, the spin parameter is the only difference. And this, so this is now there's a recent more recent paper by Abraham Hart and Marius on the structure of these of the resulting MPD equations. So this system here can be sort of massaged into the form of an MPD equation, because here in the choice of the null frame here, essentially the choice of this additional the choice of this additional tetrad leg, which determines the plane of where these complex null vectors live. So the polarization plane, I mean, that's not really determined here by the setup. It's really an observer dependent thing, and so the choice of this tetrad, or the choice of the plane or the polarization plane here, is really means that you're introducing an observer, and so. And this is what we see here as well. And now, to put this in an MPD-like form, we can introduce the spin tensor, and then we can rewrite the equations of motion in this form. And this can be obtained from the MPD system by using the spin supplementary condition like that. And this is, there are many different spin supplementary conditions that have been studied, and this has the name of this is sometimes referred to as Coronel-Desi Papapetru. and here, a very important point here is that the system here, the equations of motion here, depend on the choice of the observer vector field, and this is simply a fact about the MPD equations, that the choice. So as I said earlier, the centroid in a relativistic situation, the centroid depends on the state of motion of the observer, and the spin supplementary condition essentially refers to the choice of centroid. So if you have a massive particle, then the choice of centroid is more or less determined, so to speak, and this leads to the Tulchev spin supplementary condition. But for a massless field or in general, if you make a different choice of centroid, you can get different resulting trajectories. And here, the analysis shows that the equations of motion that you get will involve the observer vector field. So this means that different observers will see different trajectories, or will observe different trajectories. But the effect of the choice of observer is on the order of, it's on the order. So it's not arbitrarily large. It's on the order of the wavelength. So this is something that can be sort of understood and analyzed. And so here's an example of this Wigner translation, which is this refers to the deflection of the centroid depending on the state of motion of the observer. And so this is an example of polarization-dependent trajectories for different observers. And so if you have just a static observer, then the static observer will not see a deflection, but an accelerated observer will see a deflection. But the deflection is sort of on the order of, at most, of the order of wavelength. And so here's an example of motion of the trajectories in the Schwarzschild space-time. And so here you have the examples of the trajectories. So the green one is just the null geodesic, and the red and blue are trajectories of different circularly polarized light. And here there's an extrinsic orbital angular momentum which comes about because there is this object in the space-time, and the relative position of the or the direction of propagation of the beam relative to the location of the object, that causes the spin-orbit coupling that causes the deflection of the orbit. And so this deflection is, of course, extremely small, but and in these pictures this has been exaggerated just for visualization. But let's see. Yeah, so here's another image of the same thing, but now this now illustrates the observer dependence. So and one can argue that the observer dependence can be in some situations is small relative to the overall deflection of the trajectory depending on the polarization. So in principle, this would be observable. The practice, in practical terms, observation is difficult because of the fact that this is an effect of which is order 1 over frequency. So you need to go, depending on the scale of the object, you need to go, for example, in the solar system, you would have to go to sufficiently high frequencies that these observations become quite difficult. But this remains to be seen, so to speak. Let's see here. Yeah. Okay. So so just to conclude, so this is as I said in the beginning, this is really, to some extent, a formal analysis. So this is, like a small divisive problem, and we do not have we do not have the estimate, so to speak. We have the formal analysis of the equations of motion, but I think there's a whole interesting field of problems that opens up, by this analysis, and there's already, there's quite a lot of literature, Teufel and others, on these topics, where people actually do have estimates, and I think this would be quite interesting to perform in these more geometric situations. So there's a lot of work on like Schrödinger type equations, but here this is quite a different situation. So there's a small divisor problem. There's semi-classical analysis. A question is the time of validity of this WKB ansatz, and what beam approximations are valid, and what beams, how do beams perform in a situation where you have curved space-time and so on. However, in optics, there are experiments verifying that these effects are real, and so one can consider potential observational situations where you have gravitational wave scattering and dancing. You can look at effects on black hole shadows and so on. And the gravitational waves have much lower frequency than light. So this means that the potential spin-Hall type effects can be larger, so to speak. And there's a whole lot of interesting geometry that has been analyzed, in particular in the situation of Yang-Mills fields. And this still needs to be completely clarified, so to speak. What's the relation between these MPD type equations that you get and the equations that have been studied by Sorio, Sternberg, and Wong in other situations. Yeah, so that's all I had to say. So thank you very much.